All right, next topic in stoichiometry is percent yield. So percent yield is a calculation that we do when we do experiments to basically determine how much product did we actually make versus how much we thought we were going to make. So when we talk about percent yield, we generally talk about theoretical yield and experimental yield. So theoretical yield, when we talk about that, is how much I expect to make from my stoich calculation. So this is when I do my stoich, I'm assuming I use all of my reactant and I turn into product. How much should I be able to make based off of that? Whereas experimental yield is when I actually do my experiment. How much product do I get? Okay. So generally what you're going to find is when you do an experiment, usually our experimental yield isn't going to match up with our theoretical yield. Okay, we like to think that it is, right? We like to be like, oh, we're going to go in the lab and we're going to do a perfect lab. Everything is going to turn out exactly the way we want it to. Okay, the reality is you should never get a perfect yield. There are many factors completely outside of your control that we're going to talk about in the next couple of slides that should make it so you never get 100%. So what that means is if you do get 100%, you've actually messed up enough to counteract everything that was already there that prevented you from getting a 100% yield, okay? So talking about what some of those things are that are inherent, that you have no control over, that are going to prevent you from getting 100%. So one of those is competing reactions, right? Generally, we like to think that when we combine two reactants, there's only one possible reaction that can happen. And combustion, I would say, is definitely one of the classic examples of that. If you think about every combustion reaction you've ever written, you only write it forming carbon dioxide and water vapor. But you also know, just from life experiences, that you're not supposed to run your car in a closed garage or run a barbecue in a closed garage because it makes carbon monoxide. Well, if you think about the combustion reactions that we've been writing, there's no carbon monoxide in there. But that's because when we write combustion reactions, we're only writing complete combustion. There's another type of combustion called incomplete. It uses the exact same set of reactants. It uses whatever your hydrocarbon is and oxygen. The difference is that in incomplete combustion, some of my products don't turn into CO2. Sometimes what happens is I don't have quite enough oxygen, or my sample is burning so rapidly that it's depleting my oxygen before it can be replenished. And what happens is, although I make water and I make carbon dioxide, I start to make some other products. And those other products are carbon monoxide and also just straight carbon. Right? Notice when you like blow a candle out or when you first light a Bunsen burner, there's usually that bit of black smoke. And then we always talk about, oh, turn the Bunsen burner until you get that nice double blue cone. We don't want that big messy orange-red flame. And that's because when we get the double blue cone, we have complete combustion. When we have that messy orange flame, which think about your barbecue at home, you definitely have that messy orange flame, you have incomplete combustion happening. So here we have a classic example of if I assumed that my combustion reaction was a complete combustion, and I didn't account for the fact that there were other things happening, that would prevent me from getting a 100% yield because I haven't actually accounted for where all of the carbon is going. Because some went into CO2, which is where I assumed it all went, but some also went into carbon monoxide and some also just went into that straight carbon. Okay, so that's one big thing that can prevent us from getting 100% yield. Some other ones, which unfortunately, because we didn't really get a chance to do much labs this year, you didn't really get a chance to experience these. So one of them is a slow reaction. Generally at school, we're limited by the fact that we have 85 minutes to go to the lab and do an experiment, clean it up, and be out of there. So usually we try to pick fast reactions so that they're done really quickly. But sometimes we just kind of run out of time and we're just like, oh, it's done, even if it's not actually done. At which point we may find that the conversion of reactants to products may not actually be done. Another big one is when we collect and transfer things. We're often going to lose stuff. Okay, you're going to find we usually stir things during a reaction. If you take that stir stick when you're done stirring and you look at it, it's usually going to be coated and stuff. But when we go to weigh our products, we're not weighing what's stuck on the stir stick. So we've lost some material to transfer. Okay, same deal. Sometimes we'll like change from one beaker into a different type of container, right? When we talked about in the solutions unit how to prepare a solution, we said you would start by making it in a beaker and then pour it to that volumetric. Well, if you don't rinse that beaker really well, you're going to lose some of that solute when you transfer it to the volumetric. And so there's another transfer point where something hasn't fully moved over. And so now your calculation assumes that all that mass is there, but it isn't because you've lost some. Okay, you also find sometimes when you like heat things, things will kind of blow over, make a little bit of a mess. And again, you've lost mass. So another one, which is something entirely outside of your control, is how pure reactants are. Okay, when we buy laboratory grade chemicals, they're not 100% pure. So we assume that when we go and collect, let's say 5 grams, that all 5 grams of that is actually reactants. But the reality is that it isn't, right? Maybe only 95% of that is actually reactants. But we don't know what percentage of purity our reactants have, and we assume they're 100% pure even though they're not. So that means when I do my theoretical calculation, I'm going to get an answer that corresponds to 100% purity, even though I don't actually have that. Okay, and another reason, which is actually a really major thing, makes up 2 units in Chemistry 30, is that not all reactions go to completion, right? Think about in the last unit. Sometimes we use single-headed arrows and sometimes we use double-headed arrows. Many reactions, we find that when the reactants react to produce products, those products, to an extent, react back to give us those reactants. And so then we don't have that 100% conversion, which when we do stoich, we assume all reactants turn into products. But if we have a double-headed arrow like you have in this one here, that's not true in this case. Not all of this gets converted into this. Only some of these reactants get converted into products. When you get into Chem 30, if you're taking that next year, you'll see that we look at how you calculate that, and it's quite different. It's not going to be a stoich calculation because stoich assumes that a reaction goes to completion. So how you actually calculate percent yield, it's a pretty straightforward calculation. It's experimentally how much did I get versus theoretically how much did I get times 100, right? So similar to how you guys calculate marks on things, right? What you got versus what you could have potentially got. So experimental, what I get from my experiment when I weigh everything at the end, and theoretical is what I got from my stoich. So for the most part, you're generally going to find that your percent yields are going to be less than 100 because of the factors we talked about. It is in some cases possible to get a percent yield over 100%. Okay, when that happens is usually one of 2 scenarios. Either we were letting the sample dry so that the water would evaporate, but maybe all the water didn't evaporate, and so that I'm getting a mass higher than I should because I still have water in it. Or not all of my reactants turned into products, so I'm seeing that I have more mass than I should have because I still have a bunch of reactants left over in that container, okay? So generally it's going to be less than 100, but there are definitely some situations where it can be greater than 100. And if we were at school doing some labs, you would see that we had some that were greater than 100 and some that were less than 100, right? So one of the challenges that some of you guys are going to have this semester is just that you don't actually get to see things, right? I know we spent a lot of time at the beginning of the year talking about how one of the nice things with some of these units of chemistry is that you actually get to go to the lab and you actually get to see it. And a lot of times when you actually see something, it's like, oh, now this makes sense. I get what's happening. But obviously, circumstances have changed and we are not at school. We are all hanging out at home trying to get through some chemistry stuff. Okay, so let's look at some examples. So when 2.43 grams of magnesium is burnt, burning magnesium is always fun. Don't recommend you do this at home, but you can definitely go watch a YouTube video if you've never seen it. It makes a really bright white light. So it's burned and is found to produce 3.95 grams of magnesium oxide. So this how much I got from my experiment. Okay, it told me that we produced 3.95 grams of magnesium oxide. Here, it's telling me what the theoretical yield is. So some questions you're actually going to have to calculate that, right? So theoretically, I could have calculated that from this 2.43 grams, just doing a STOIC calculation. But in this case, I don't have to, right? So here, it has given me the theoretical value. And here, it's giving me the experimental value. So givens-wise, I already know that the experimental is 3.95 grams. And I already know that the theoretical is 4.03 grams, right? If we think about what our equation is, it's that the percent yield is equal to our experimental over our theoretical times that 100. Okay, and we basically have everything we need. So we just need to plug some numbers in and actually calculate this. So we're going to take our 3.95 grams. We are going to divide that by 4.03 grams. And then we are going to times by 100 because that's what we do when we are calculating percent. And we get 98.0%. Okay, so percent efficiency is not an equation that is given to you. Why am I saying percent efficiency? That's not percent efficiency, it's percent yield. So percent yield is not an equation that is given to you. So you do want to make sure that you know how to calculate that. You're going to see we're generally going to talk about percent yield, and then later on we are going to talk about percent error, and they're two slightly different things, okay? But percent yield, same way as you would calculate a mark on something. Experimental over theoretical times 100. Okay, so here's our next example. So when 5 grams of copper is placed in a solution of silver nitrate, a single replacement reaction occurs. During the experiment, 15.5 grams of silver is obtained. What is the percent yield? So we're going to need to write a balanced chemical equation for this one. So we have copper being placed in a solution of silver nitrate. Okay, we have a single replacement, so we are going to make silver and copper 2 nitrate. Okay, and copper 2, because when we're not told what the charge is, oh, what did I just do? I have no clue what I just did. Hold on. Okay, so copper 2 nitrate was what I was trying to say before I had some issues. And this is going to be aqueous. So balancing wise, we need a 2 and we need a 2. So givens, we were told 5 grams of copper. So molar mass for that, 63.55 grams per mole. Okay, so what are we looking for? We were told 15.5 grams of silver is obtained. What is the percent yield? So we need to figure out what's the theoretical mass of silver that we could make. So molar mass for that, 107.87 grams per mole. Okay, so we are calculating the theoretical mass of silver. We already have the experimental mass, and then we can calculate that percent yield. So calculating the mass of silver, we're going to start with the molar mass of silver, so 107.87 grams per mole of Ag. Okay, we need to get rid of moles of Ag, so we're going to use our ratio. So times 2 moles of Ag. That is going to be over 1 mole of copper. Okay, from there, we can eliminate moles of silver. We need to get rid of moles of copper. So to do that, we're going to use the molar mass of copper. So we're going to go times moles of Cu over 63.55 grams. That lets us get rid of moles of copper. Then we need to get rid of the grams of copper, so we are going to use that 5 grams. All right, so now that we have that, we can go about actually plugging this into our calculator and determining what that theoretical mass is going to be. So 107.87 times 2 divided by 63.55 times 5. So we get 16.97, and the number keeps going. Okay, because this isn't my final answer, I don't want to round. I want to use that whole number. Okay, but now that I have that, I can calculate my percent yield, right? Because we've established that it's experimental over theoretical times that 100, right? And so now we have all those pieces, right? The question gave us the experimental. So we had, what was it, 15.5 grams. Right, and then we are going to, still an underline up, times by 100, and then divide by, I don't want to do that, 16.97, making sure that on your calculator you're actually using that answer button, right? So we're going to do 15.5 divided by answer times 100. Okay, now we're going to actually round for significant digits because we are at the end of the question. So we're going to go 3, so we get 91.3% as our answer, okay? So this is kind of the biggest those percent yield questions get, right? The previous example, it gave you the theoretical and the experimental. This one only gave you the experimental, and you had to go ahead and calculate the theoretical to determine the percent yield, right? You'll also see some questions that will give you the percent yield and then ask you to determine either the experimental or theoretical. But again, they would have given you 2 of those things, and there would only be that third one for you to be looking for. So that is your percent yield and basically how percent yield works.